Hello, my name is Choong-Hoon and I'm a principal engineer at Samsung Research. This paper studies the feasibility of using bone conduction response patterns to authenticate smart glass users. This work was done in collaboration with UNIST and KAIST. New form factors like smartwatches and smart glasses have started providing security critical features, and user authentication is becoming really important. But such wearables have limited input displays, and entering pins or patterns is going to be really difficult. What about existing biometric solutions? But they have security issues. So face fingerprints, they're all vulnerable against spoofing attacks. There are usability issues too. It's still hard to perform biometric authentication on out-of-sight devices. So our objective is to develop a biometric authentication system that does not require users to perform complex actions and is robust against spoofing attacks. And our solution is bio-acoustic-based authentication. So bone conduction speakers are used to play an initial cue signal on the head, and bone conduction microphones are placed on the other side to record acoustic responses. And we use unique acoustic response patterns to identify individuals. Our intuition is that response patterns will be uniquely different because human skulls have different shapes and bone structures. During enrollment, users need to put on the glasses about 5 times, and we collect about 5 samples per donning. We then use these reference signals to extract MFCC and PSD features and train a binary classifier. So during authentication, users put on the glasses and the cue signal is played automatically. Response signals are collected through 2 microphones. We extract features from them and use the classifier to authenticate the user. The first study was conducted to answer 2 research questions. First question is, can audio signals transmitted through the skull serve as biometric? And the second question is, what are the optimal microphone locations to collect signals from? To conduct the study, we constructed a headband prototype, which has microphones mounted on the brow, temple, squamous, and left mastoid locations. The bone conduction speaker is mounted on the right mastoid behind the ear. We conducted a single session study with 25 participants. Participants performed 5 donnings, and each donning we played 3 types of cue signals and recorded 20 samples per cue type through 4 microphones. For evaluation, we randomly selected 2 groups, 15 imposters used for training a binary classifier, and 10 genuine users for evaluation. First 4 donnings were used for training, and the last donning was used to evaluate force direction rates. Samples from other 9 genuine users were used to measure force acceptance rates. We repeated this 100 times and measured the average. So here are the equal error rates for 4 microphone locations and microphone combinations. Brow showed best performance among single location systems, and combining multiple locations significantly lowered the error rates. A brow and mastoid and brow and squamous combinations showed consistent performance across all cue types. To determine optimal microphone locations, we looked at energy transfer intensity, consistency of PSD data, and effects of combining multiple locations. Energy transfer intensity was measured using a transfer function. So a brow and mastoid, which are the more bony areas, showed high intensity. Consistency of PSD data over multiple donning sessions was measured using a Wilks lambda. Again, brow and mastoid showed high consistency compared to temple and squamous, which are more affected by hair obstructions. We also analyzed 9 participants who showed poor performance on at least 1 location. But all of those participants also achieved force reduction rates on at least 1 location. So with an optimal strategy for combining microphones, theoretically, all users can experience consistently low force reduction rates. And for 2 participants who failed sessions for brow, mastoid locations provide reliable data and vice versa. So as a result, brow mastoid combination stabilized force reduction rates for all failed cases. Hence, our recommendation is to place contact microphones on the brow and mastoid, which achieve a high energy transfer intensity, show consistent PSD data, and are effective in complementing each other. The second study was designed to evaluate multi-session performance. We developed a glass frame-based prototype to reliably conduct the multi-session study. Based on the first study findings, we located microphones on the brow and left mastoid. We also added in-ear microphone to compare performance against state-of-the-art system. We recruited 15 genuine users and 15 imposters. After the first visit, genuine users came back for 3 more recall sessions with a minimum of 30 minutes between 2 sessions. In each session, we played 20 samples in normal condition and 20 more samples in a noisy condition with some background noise. Then we measured force rejection rates based on the last donning from the first visit and 3 normal recalls and 3 noisy recalls. So the graph shows RC curves by each microphone location and Q signal types. Equal error rates from later recalls are elevated compared to the immediate recalls. But combining the 2 microphones is effective in lowering the EERs in later recalls. We also show robustness to audio noise. There's not much difference in the EERs between normal and noisy recalls. We also measured in-ear microphone performance. The state-of-the-art system shows substantial increase in EERs in the presence of background audio noise in the ranges of 58 to 66%. The first graph shows high variations in the PSDs compared to on the in-ear signals. To demonstrate robustness to replay attacks, we recruited 10 new participants as attackers. For each attacker, 68 genuine samples were played on standalone speaker pressed by the attacker against their skull in 3 different locations. The attack success rate was just 0.4%, but 7 out of 17 users were compromised. We looked at the attack signals for those 4 participants and observed very low energy transfer rates on microphones that were located far from the attacker's speaker. The third graph shows very weak energy level on the attacker's mastoid. The samples were played on the brow. Such unknown PSD patterns can be classified randomly and result in authentication failures. To mitigate this problem, we tried adding those attack samples to the imposted train set and achieved 0 force acceptance rates. So in conclusion, our single session and multi-session studies show that bone conduction-based authentication is effective, immune to noise, reliable over time, and robust to replay attacks. And our recommendation is to use both brow and mastoid locations to achieve consistent and reliable performance. And thank you very much.